Today we start our last day of school, and we are not in full complete, but I hope we will stay in at least in this version until the end of this day. So we start this school from this day of the school from the lecture of Professor Ioffe.
Thank you. Good morning to everyone who had the strength to come in this ungodly hour. And I hope I will not disturb your sleeps with this lecture. And I plan that it will be relatively short. Okay, so there is a general theme of these lectures that we finally are ready to discuss what I was, the reason why I was explaining to you what we have, what are these quantum computers that we have at this moment, with emphasis of course, on what we have at Google, but most likely more general in solid state. So, so first of all, a few general words that when we talk about the quantum evolution, roughly speaking, the limit that we can simulate classically, just and really the limit, because by limit I mean what we can simulate on the best available supercomputer, which works for a few months at the cost of God knows what. So it's about 64 qubits. By simulation, I mean, of course, exact simulation without making any approximations. So the first question is sort of conceptual. Suppose, well, we have like a system of 100, maybe 200, maybe 400 qubits, and we get some results. How on earth do we check them? Why do we believe that? That is, of course, a big question, and I will talk about it towards the very end, because as you realize, what we discuss in these lectures is what we do when we do not have error correction. And since we don't have error correction, there is absolutely no reason a priori to believe our results. So we can hope, but it's not more. And then the question is, what are the results? What do I mean by result? First of all, of course, we already know, and Google showed it 5 years ago, that quantum computer, even with this very small system, can produce the result that cannot be. Yeah.
I have a very basic question.
Yeah, it's all very basic here. Yes.
What is the simulation of a quantum computer?
Oh, we just take the initial state of your. So suppose I program some evolution operator, right? That is, which is a product of individual Hamiltonians, which are either simultaneously on all gates between the qubits, right, on all links between the qubits, or maybe in order consecutively. That is sometimes so each gate is, as we discussed, is G sigma plus sigma minus plus maybe with space. So I either act with these guys simultaneously on all pairs of nearest qubits, or consecutively, because I can switch them on and off. So I generate some evolution of my initial state. And the initial state is always something simple, right? It's a product of well, somewhere zeros, somewhere ones, some trivial state in Z basis. And then I ask, what do I get? So if I Of course, you are right that you probably mean that when I ask what do I get, I can, of course, at the end of the day, I get some very complicated wave function, which is u sine of, right? So when I say simulate, of course, I meant that I get this wave function fully, which is very difficult, and then, but that is not a proper question because I cannot measure the full wave function experimentally. So what I have to ask is some more complex questions which are measurable, and in this work I guess, so if I could measure the full wave function, there will be absolutely no question to discuss, right? Because there will be no reason to do the work, because we know that for sufficient, even for less than 64 qubits, we cannot possibly produce a wave function which contains 2 to 64 numbers, too much. It doesn't fit in any, even the supercomputer. However, we always have some result, so we do not measure such a beast. Instead, what we measure is probability of a given configuration, let's say S. That is, we measure at the end of the evolution, we measure all qubits in some basis, right? And so we get some Steen's configuration, and we get many of these results. The question is if we can predict what are the probability of different bit strings. That is the valid question because that's what we can produce experimentally, and then the question is if we can simulate this evolution classically, on the classical computers. That's much easier problem than simulate psi, but it's also very difficult for these large Hilbert spaces. And then there is, if you ask about this, the problem in which you just asked me about individual bit strings, that is, what is the probability, what is the, to predict the probability of the bit strings, then it's a problem which is still very difficult for a classical computer. And so there was some mathematical work showing that indeed around this point, you cannot, there is a barrier which a classical computer cannot achieve. Even though it's not a full wave function, but only this probability. So that's what I mean by simulation. Of course, it's a...
question. There are a number of possible bit strings.
Yes.
Is just these 2 in 64.
Yes, exactly.
So, in which sense it is simpler? Because you do not want to measure all probabilities.
No, some, of course. You measure, you start to generate some bit strings, and so you can say about probability of some bit strings which are the most likely to occur. And you ask which of these bit strings and it becomes a very difficult problem when U is, roughly speaking, the most random unitary matrix. That is, to apply gates so that this U is practically indistinguishable of being completely random. And then, well, then you ask this question, and you see that the barrier is about that. So of course it is. That's exactly was my main point, right? That I wanted to make next. That this is completely useless, right? Who cares what are the bit strings produced by random evolution? So it's like sort of predicting the toss of the coin. I toss the coin and okay, I get a couple of, and suppose I do not do it completely randomly, but there is some intrinsic preference, but after all it's just tossing of the coin. It doesn't have any physical meaning. So that's why, even though it's a remarkable result that we can have quantum evolution that cannot be introduce classically, the value from the point of physics or application of this result is nothing. It doesn't teach us anything about physics or life or whatever. So in this talk today, I would like to focus on other problems, that is, which are B and C. That is, can we simulate some interesting quantum physics systems that are interesting regardless of the existence of quantum computer, and discover something new, or maybe verify something that we were not sure about? And the answer is probably yes. And that will be my main argument today. And then there is a very tricky question, which is C. Suppose we do these simulations and discover something that we cannot verify classically. That is, let's say that at small system sizes we we have a mess, we cannot figure out what's going on. We simulate large qubit systems of a few hundred qubits. We find something new, but how do we know? How can we trust this simulation, even if we discover something new by that? That is a very non-trivial question. I will argue that about point B, we gradually go there. We have already some little discoveries, which my colleague Pedro Ambrushani terms discoverino. They are small discoveries, and but we gradually get them larger and larger. So hopefully we'll get them. But so far they were all possible to check by numerical simulations. Okay, so that is just a general outline. No? Okay.
Maybe the stick is poorly plugged.
What?
Maybe the stick is poorly plugged in, no?
No. Okay, I can always do it. Oh no, I think it's just a computer that goes great. Like this. Interesting. Like this it works. So let's recollect what we have. It is we have basically, as I said, at the moment, roughly speaking, 100. In the near future, a few hundred qubits. That is, each gate, or equivalently, the interaction. Gate is 10 nanoseconds, or the interaction is about 10 or 20 megahertz. So the single qubit gates are 10 nanoseconds. 2 qubit gates are slightly longer, but that's a typical scale. And as I told you a few times, characteristic lifetime of the qubit is of the order of 100 microseconds. So naively, it means, as we already discussed, that we can do about 10 to 4 gates, which is already very good. However, the characteristic, the dimensionless time of our problem is of 10 to 4. However, if we want to simulate something that is difficult to simulate classically, what we expect qualitatively that these wave functions are very fragile. Because if they're not fragile, then some clever person can invent efficient classical algorithm to simulate it. Because if something is robust, well, you do some trivial approximations, well, trivial or non-trivial approximations, and you simulate them classically. Okay, so if they are fragile, then we cannot afford that even a single qubit decays. So effectively, we immediately reduce the number of the available time to these much smaller values. So And that, of course, is very bad because, especially if you look at the lower limits here, we barely have enough time for the quantum information to propagate through our system. At the moment, it seems that the only way to get something interesting is to consider only the propagation in which we can check that not a single qubit decayed, which is called as error mitigation. That is, we just create the state with a number so that if our U conserves the number, conserves the total magnetization, then we can check at the end of our evolution that the number of ones in our wave function remains the same as before, and then even if it happens with probability, let's say 1%, so we throw away these 99% of the cases, but we are sure that not a single decay process happened during the evolution. And so this fragility of the wave function remains intact. So that constraint of error mitigation is very important. Okay, so that is basically a general picture where we are and what we need to consider to do something interesting. We are basically at the very border, I will say, of the somewhere here, well, at the interesting physical phenomena that we can simulate. And if we increase the error rate, decrease the error rate, and increase the system size, roughly speaking, by a factor of 4, then we can do also quantum chemistry, but it's not the subject of my talk. So we are really at the regime at the moment, and for the next few years we will be here, not many, but few, where we cannot do something practical, such as quantum chemistry, but we can do some many-body problems which are of fundamental interest. Let me just go through the very simple work that we did a few years ago in Google. So that was to show that indeed these simulations are possible, and so the results are good. I mean, very precise. So that's of course very elementary work that you can actually the computation that is involved you can give to an undergraduate student to check or to do just. So the idea was that we have just one qubit in state 1, and so this of course qubit in state 1 can be regarded as a particle which hops on one-dimensional chain, and we moreover consider use the closed loops and put some synthetic flux in this loop because we could do that because we do the gates. So that was discrete evolution in which we applied the gates on we applied these operators alternatively on even and odd links, and we just studied the spectrum of this problem just to see that that the results are correct, exactly what we expect. So the work was mostly done by Charles Nail. Of course, you realize that this is always the work in which many people involved, because even if there is a particular person like Charles who does this particular work, there is enormous number of people involved in fabrication of the device, in controlling in setting up the electronics, and so it's really the collective effort. It's very similar to elementary particles in some sense, where you need a big group to do the work. But the person who did the actual work was Charles, and so he chose some particular chain of qubits in this big system, and so in the he applied the gates, which are shown schematically here. That is, he applies the gates on this side, on that. These are single particle gates, and these are 2-qubit gates, and that was, and run the system for some time. So as we also discussed,
Sorry, could you?
Yeah.
What is the upper plot? What is the?
what was this?
So no, this one. What is this?
Ah, yes, look, this is the actual device, I'm sorry to say. So the actual device is always two-dimensional array, right? So we have the qubits which are connected by the couplers here, right? So this is the qubit, which in this design was really like a cross. So if you remember, originally when I was talking about the qubit, I was drawing something like that, which is actually a qubit, but it's not easy to do that, to couple them like that. So in fact, when you couple them, instead you do something like this. You have so in this design it was this guy. So these are the same as blocks here, and here you have a little resolution junctions like this, and there is a squeeze so that you can control the frequency of the junctions. So it's frequency controllable qubit. Now the idea why we do that is that this in fact forms this leg of the cross forms a capacitor with the next qubit. So you can imagine something of this sort. That when you look from above, it's a parallel plate capacitor which forms a very strong coupling. If you remember, I explained you before that, well, theoretically, we would like to have a capacitance matrix like that, right, where C0 is the self-capacitance of the qubit, and this is coupling to the another qubit. But in fact, we have so many couplings that practically all capacitance is in the coupling, and that's how it looks in reality. That sort of that all capacitance is in the coupling of this qubit with the coupler here.
What is the red color?
So this one. Oh, that's actually the qubits that I use. The rest are just silent. So that's just how he chose the path for this one-dimensional. So nowadays, when we do one-dimensional problems, this was just the first work. But nowadays, when we do one-dimensional problems, we really wiggle all the way, so we cover everything with our one-dimensional chain, to make this one-dimensional chain as long as possible for a given system. And we can go up to, well, maybe not all the qubits that we have in the system, but more than 70. So it's big thing. Okay, so so where we were? Yes. So there are two possible experiments that one can do. Is first create particle at site 1, and then the map probability. Then to take the Fourier measures probability where it propagates. That's of course in the normal physics language is nothing but the calculation of the square of the Green function. That is possible, perfect, but you see that if we are after the spectrum, what we get here is a convolution, because it's a square in the real space, and so for it's a convolution in the energy space, and so we have to do some work to extract the levels from this convolution. But sorry, but it's possible to do. So there are many peaks, and then we have to really I figure out how to identify them, which is not a big problem when you have a small system, but quickly becomes a mess when you go to larger systems. So it's much better to be able to compute the green function. It's directly, as actually we discussed before, and indeed this green function can be computed, as I explained you, if we create this state, and so which is, and then we measure sigma x, which is nothing but the real part of the propagation, which is directly the same as the green function. Okay, so that we discussed last time, so I do not want to spend more on it. So the actual analytical computation of this problem is even shamefully trivial. That is, we take the Fourier transform of this evolution operators, we get these two matrices, then we multiply them, again, what can be easier, and diagonalize. And we get this spectrum of this problem that we expect. Not a rocket science at all. So, so we measured, and we found, so Charles measured, and so he found the spectrum, which is, as you see, this is not the fit. There is theoretical prediction without any fitting parameter, and that is the data points. So, so then the accuracy is extremely good. So that, and again, the key to this accuracy is post-selection. That is, we always throw away all realizations in which this particle is active. Okay, so that was the first result, and actually this result was obtained back in 3 years ago when our the coherence was much, much worse than it is now. So you should realize that since then the quality of our evolution improved dramatically. Another check that we are that we get what we expect is to add the magnetic field to our evolution. That is to add the phases, which we can do, and to the closed loop to check what is the energy as a function of this phase, because a phase, of course, acts as a shift of the sorry, not phase, the gauge field. What it does is changes the effective momentum, as always. Here, of course, is U over E over C is 1 in this units, and so what we see is that the flux or the vector potential changes the levels exactly so that the first level becomes the second, and after we go the full over the full period. Boom, boom, boom. Now, and then we can do even more. We can check that if we start to apply some disorder, then instead of level crossing, which happens as with the momentum equal pi, we have the splitting. So everything works perfectly as one would expect in the theory, and this, well, of course, the theory is very simple. So, so we can study this level splitting, and so it's the conductance, everything. So of course everything works out, but of course it's not a big deal because it is really non-interacting single particle problem, which is, as I said before, at the undergraduate level. So, but our quantum computer could reproduce undergraduate work. So, okay, so that we discussed before. So then, let me talk about little work that we did more recently. It was mostly done by Alexis Morvan, and with the help of other experimentalists that you can see here. So let me first explain you why this subject is generally interesting. So yes. So that's the subject is related to the very old problem of appearance of chaos. So as you, of course, realize, almost all natural phenomena exhibit some amount of chaos, and that was originally realized by Newton. And he didn't like this realization at all. That the system of planets which rotate around the sun, because the planets interact with each other, the motion will be very complex. He didn't come up with the word chaos, but he was thinking that it's not a good thing. Correctly, he was thinking, and so he said that he needs God to adjust the planets so that the chaos doesn't appear. So, in this respect, you can only recollect this famous discussion of Napoleon and Laplace, I think who was, right? Napoleon asked Laplace where in his theory of planetary motion there is a place for God, and Laplace answered that there is no place for God, which was completely wrong. There is a very important place of God because the motion of planets is almost chaotic, so it really requires a fine-tuning to prevent the chaos that will make all the life on the Earth impossible. So, so the general question of stability against chaos is very interesting, and from the viewpoint of classical mechanics, and also, of course, quantum mechanics. So you can ask the same questions. That suppose we have stable motion, or in the system like this planetary system, and we introduce some perturbation which violates the integrability, which is responsible for the stability. So what happens? So in order to study what happens, and actually, to be honest, this was not the original motivation in this work. We just thought that it's trivial, and we were very surprised with the result. So what we did was the following. Our toy model of the planetary system is the same chain of qubits that we discussed before. Only now we do not study a single particle. We study a many, we study a many-body evolution of this chain under the action of this clear Hamiltonian that we discussed with you a few times before. The fact, for this problem, as we realized, the presence of this term is basically irrelevant. It just makes, for this problem, this problem, this term is relevant, but not for, it does not create the chaos itself in this sense. So we again do the same procedure that Charles did for the single particle chain. That is, we apply this Hamiltonian consecutively on even and odd bonds. The point is that even though it is a discrete system, as Thomas Prosen realized some years ago here, the system is integrable, so it can be solved. But of course, the hairs, I'm sorry that we call these guys hairs for obvious reason, and we apply the gates which couple to these hairs from time to time. The hairs violate this integrability. So this a posteriori, it looks like a very good system to study the the effect of breaking integrability, because we can break it in a very controllable way. All right. So first, that is to repeat what we have. That is, at the single particle level, we have these two evolution matrices. We have this spectrum that we discussed before. But there is now the reason why I bring this up again is because I would like to emphasize one very important point. That you see that this spectrum covers almost all the Floquet zone. You should realize that now, because we have a periodic evolution with, we have a Hamiltonian which depends on time, but we apply gate periodically, our energy is not conserved. What we do not have anymore in this system with gates is the time translational invariance. We can only translate time by the period of our evolution. You remember that we apply gates like in steps, right? So we have a period, and the energy is conserved or is defined up to 2 pi over t. So this is this is Floquet equivalent of the block zone in the conventional solid state. So that as you know, the momentum in the normal lattice is conserved up to the 2 pi over the period of the lattice. Similarly, the energy in this problem is conserved up to 2 pi over the period of our gates. So now the important point that I would like to draw your attention to is that the band of the excitation covers almost the whole period. So you see, so the period here is from -12 to half. So that we have a single excitation covers almost all possible energies. What does it mean? That two excitations cover really everything. That is, for the two excitations, we can have the system with two excitations can have all possible energies available in the system. There is no such notion. Why I'm talking about it, because normally, when you have two particles, imagine that you have two particles with some spectrum. And because there are two particles, you create a bound state somewhere here. Below the band of this particle. Then you say, oh, since this energy is negative for two particles, these particles cannot go far away from each other, because then if they are far away from each other, they do not interact, and therefore the energy will be positive, and in fact the energy is negative. It's forbidden by energy conservation. So bound state of two particles in normal life is completely protected by the energy conservation, because it's below, it's in the forbidden band. However, here in this Floquet problem, we do not have anything like that, because the energy is conserved up to this 2 pi over t, and therefore there is no notion that we can get, there is no forbidden band at all. So nevertheless, nevertheless, we do have a formation of the bound states, and this formation is, if you wish, a miracle. It's a miracle which is due to the integrability of the system that was discovered by Igor Alenin. that the exact solution, apart from the well, some phases which are not so interesting, also describes the bound states of these two particles. For any number of particles, in fact. For two particles, you can do the direct computation, which are a bit messy, but not so difficult. And for 3 and more, you need really to do the full beta ansatz, which I'm not going to describe today. That is yeah. So well, there are some little details about how to see the formation of two particle bound states, and so the convenient thing is to introduce these variables, but probably it's not so interesting for you. It's just some algebra. Yes.
Yeah. You're talking about bounds.
Yeah.
But you need interaction.
Oh yeah. There is ZZ interaction.
This is.
Yeah. So
they forgot to mention it.
Right. So you see that I said that ZZ interaction, the crucial thing in the beginning is that ZZ interaction does not violate integrability. But of course, ZZ interaction leads to the attraction or repulsion between the particles. So, and it is, so yes, maybe I should have emphasized it before. Let me go back. I forgot about it. That so ZZ interaction translates in non-trivial value of the phase here. That is, if two spins are up, then we get additional phase. That's nothing but ZZ interaction. All right. So fundamental computations are boring and quite messy, but the result is that you get these bound states. And so now the next sort of conceptual point is that how do we see these bound states? Of course, we can do the same thing as before, just to measure the propagation of the density. However, it's much more interesting to study to do the following, to form these operators, which are acting, which is sort of simultaneous creation of the particle states, do the form the state similarly to single body particle state, form a state which is superposition of nothing and such monster created, and then measure the sigma x operator. So, so as a result, what we see is exactly the property, exactly what we measure is exactly the green function of this corresponding to this combined object. Of course, this is not the sigma is not the operator which creates exactly the bound state. We just create two particles close to each other, so it has some overlap with the bound state, but it is not the bound state itself. It's just something, poor man approximation of the bound state. But since it has overlap, we should see the large peak to the bound state, if it exists. And of course, we see small peaks which are due to the independent particles, which we created by mistake, because this operator creates not only the bound state but also the scattering state. Okay, so that was the main idea, and this is some numerical simulations of this idea that indeed shows how it should look in the simulation, in the numerical simulations. You see some peaks, and then one huge guy, which is much larger than everything else, which corresponds to this bound state. So numerically it works, surprisingly. And so, yeah, let's first skip it. Let's go to the actual experiment. In the actual experiment, what you see is that we can do this.
Sorry, can I just ask?
Yes.
So all up to now was just two spin flip. or how?
Right, but this can be,
It's a particle.
it can be also always generalized to 2, 3, 4, 5, whatever. Just the analytical computations become more and more tedious.
Sure, but the analytical calculation, the actual calculation to show is two particles.
Right, but you know, but to show 3, I will need to have many more view graphs with just algebra, algebra, and algebra. So, but just believe me that this problem can be solved analytically for any number of particles. Just the solution becomes extremely cumbersome. And that's exactly what Igor Aleni did. But in fact, in order to compare with experiment, we had to do numerics because what he did was for infinite system, and to see how these states are modified for finite system, analytics becomes terrible. Yeah. So you see that this is the first thing here is this very trivial measurement in which we create simply particles next to each other. We don't do anything non-trivial. And so we just see that this, when we created particles, well, let's say here is just one particle, it propagates here. Yes, maybe I should explain something simple. That because we have a, so imagine that we have a particle with epsilon of p. Then epsilon of p means that, well, some particular epsilon of p. Then it has some maximal velocity, which is here, the epsilon. So what you will see in a real experiment or in simulations, doesn't matter, is that you will see that there is some maximal velocity with which a given particle propagates. There is nothing here because there are no velocities higher than this maximum. So here, when you have two particles, of course there is a chance that you created them independently by mistake, but there is a clear line which corresponds to the fact that two particles go together and have some maximal velocity corresponding to these two particles. And so for 3, 4, and 5, and so on. Of course, for 5 it's very difficult to see anything, so we need better ways to analyze the data. So then,
could you comment what is the difference between N4 and N5 looking on the picture? It seems just the same.
well, at this picture you cannot see anything. If you look at the center of mass, you see the difference. It's just the way how to analyze it.
Excuse me, the presence of the boundaries does not destroy the regularity.
No, because the lattice was sufficient. Sorry, no, integrability, no. I don't think so.
So it's periodic. What is the boundary condition? They
Periodic.
Yeah.
Periodic.
Periodic.
Yeah. It's a closed loop. It's always closed loop. Yes, so if you analyze this data in a slightly better way, that is, you just look at the center of mass, you see very much better this maximal velocity, and then you can compare it with the analytical predictions or numerical predictions, and you see that, again, there is no fitting parameter here, and you see that the agreement is quite good.
So,
Yes, absolutely.
why does the density or the center of mass stay distributed around the linear side for many particles?
Oh, because you created them together, so most likely they will, and at zero momentum, so most likely they will not move anywhere, right? So you mean why it's mostly here, right? Mm-hmm. So look, now two things. First of all, you created them mostly with zero momentum, on average with zero momentum. Second, for many particles, you expect that the mass is huge, right? Because it's a big object. It's even imagine how if you have interaction, if you have interaction between particles, the particles mostly are like that. They prefer to be like that. How this terrible thing moves. In order to move, it has to move this spin this way, form a hole, right? Then this spin moves this way. So it's really like a caterpillar process, which is extremely inefficient. So the mass, in fact, grows very quickly with the number of particles. It's more than the proportional to the number of particles. And that's exactly what you see, that the thing becomes practically immobile, right? Here you see some dispersion, here practically not. Now, doing these correlators that I described before, we could get much more convincing results and also measure the spectrum of these particles, well, as a function of momentum, not again using this idea of creating the coherent states. And again, the comparison with the theory without any fitting parameter is quite good. So far there was nothing interesting, well, not nothing interesting, nothing unexpected here. However, the unexpected result came up when we decided to check for the stability of the system with respect to the non-integrability. So as I showed you before, we added these hairs and included this coupling, which we described by the so the swap angle to these hairs, and probably the most important plot is here or here, and you so naively you would expect that if coupling to the hair, which breaks integrability, is small, it should immediately allow us the decay process, and so we should see a large effect. In fact, we see nothing. In this particular problem, we see I remember that our main swap angle is pi over 4. So that is our sort of that's the coupling to inside the chain. It's here. But even for up to the practically almost to these values, we see almost no effect on the stability of these bound states or on the ability of remaining in the bound state even after many evolutions. We see up to 5 over 6, we see absolutely nothing. So the effect of the integrability breaking is remarkably little. And there is probably no explanation for that. We know that integrability is indeed broken in this system when we include the hairs, but somehow the system doesn't want it. I don't know. The numbers, the numerical factors are suppressing it or what, but somehow system is remarkably resilient. And that was what I will call the first little discovery in this business. Well, here we list so sort of our confusion or our possible explanations, which are none of them look convincing to us. So that's the work. And so after that work, there were some works that claim to explain or refute this. So for conclusion, well, there were 2 theoretical papers which reached opposite conclusions, and I do not have my own opinion on what is correct. So this one conclusion was that the effect goes away if we consider if we go to larger systems, larger number of excitations, and another was completely opposite, that it's very robust and they don't know why. Okay, so...
Short question?
Yeah.
Integrability is already broken when the particles are injected?
When the
Particles are inserted?
No, it's only due to hairs. You remember that I had this picture. Let me go back because it was some time ago and maybe you forgot what we do here. So the chain itself doesn't break integrability. This is fully integrable Hamiltonian, even though we apply gates, that is, we apply it step by step. And that was the fact that it's integrable Hamiltonian. If we apply it simultaneously on all bonds, it's known, it's sort of for ages, it's what Bethe discovered back in the 30s. And the fact that it remains integrable when we apply it by gates, it is sometimes on even sides, sometimes on odd bonds. It was discovered by Thomas Prosen. But once we include these additional hairs with the coupling to our chain, the integrability is broken. It's hairs which break integrability.
So then, maybe I don't understand what you mean by hairs. Are these gates or?
Yes. So we, how do I write it? So let's say we have the that's our chain. So, and here is our additional qubits. Oh, sorry, we have every other qubit, like this. So let's call this bond A, this bond B, this bond A, and so on, okay? And this bond C. This bond C, okay? So we apply UA, UB. Each U is exponential of minus A at H times T. Let's say UA is this one, UB is the same, and so on. So we apply UA on all A bonds, and then UB on all B bonds. So maybe I should better write product of UB, product of UA. We apply simultaneously the gate on all bonds A, then product of UB and product of UC on all the hairs. If we don't do that, if this is 1, then the system is integrable. So that's a total evolution. It's one step of our evolution.
So the bonds are now no physical coupling, yet only symbolized where
Sorry, this is.
the bonds are a priori no physical coupling, but
Yeah, they are physical couplings.
so A and B couplings are some, is it some capacitive coupling that's
Yeah, it's always the same capacitive coupling.
But
It's just the question is that we draw this, well, let me simplify it. We draw this chain on the two-dimensional array of qubits, and then we put here additional, because we know it's at the beginning it was two-dimensional array. So we draw the chain, and we add to this chain, when we want, some additional qubits on the side. These couplings were always present, but we can switch them on and off because you remember we have these couplers, right?
Yes, but do you switch them on before you insert the particles and measure these?
Oh no, so these are gates, so we always switch them on and off, right? This is not continuous evolution. These are gates, so that what does it mean that we do this gate? We do this evolution. Let's say that this is our bond A, right? So when we do this evolution, we just, so in here, in reality, we have this little coupler, how do I draw it? This little coupler which sits here, which is another transient, right? So what we do is that this coupler G, which is provided by this coupler, is G squared, the intrinsic coupling, divided by energy of the coupler minus energy of the qubit minus G naught, right? So what we do is we move the energy of the coupler down. So when I say that the coupling is off, it means that the energy of the coupler is very high, so that these two terms cancel and the effective interaction is zero. When we say switch on, we move the energy down, so this becomes small, well, relatively small, and so we have total interaction. Then this interaction works, right? But all others are switched off. So, of course, we do it simultaneously on all A bonds simultaneously, then on all B bonds simultaneously, and then if we have pairs on C bonds. And then so that's one step, and we of course do many steps to get the full evolution after a long time. Okay? Yeah, so that was a little discovery that was done, and as I said, the jury is still out what it means. Okay, these are these intermediate conclusions for this work. So now I would like to switch gears and talk, yes, Discoverina, about natural problems that we might be able to do with. As I argued for all this time, we are limited with this Hamiltonian, and so not so large the and with a relatively small number of neighbors. So here is my list of problems which look most interesting or most likely to be solved in a near future with given these constraints. So, so the first, I will spend some time explaining to you what is this first problem, because which is the properties of both the liquid and semi-quantum regime, because it's relatively unknown, although it deserves to be known. It's as always the problem. The problem is that this particular riddle existed for so long that it almost became forgotten. So then there is a second separate subject that we can study, which is the formation of the bosonic quantum Hall effects, for which we need non-trivial phases. And so, and also there are problems that that I'm not going to talk much about today, which is weakly non-ergodic behavior in one-dimensional or pseudo-one-dimensional chains and decay of high-energy states that we work together with my colleagues here and of course. So that's my list, and I would like to spend most of the time today, remaining time today, which is not that much surprisingly, on this first problem, which is, I believe, quite remarkable.
At this point,
yes,
just
of course.
Are you going to explain at a certain point how you reach low temperature states, somehow semi-reliably?
Semi is correct word. Yes. Well, I didn't plan to, but I can do. And that's exactly the work actually that my colleagues did recently. I didn't plan to talk about that, so I don't have slides, but let me explain you what they did. So that's actually a very good point. Maybe I should have talked about it. So, yes, we have our Hamiltonian, which is written here. Forget about the phase. We do not going to so phase equal 0. All phases are equal 0, and so the ground state, of course, is ferromagnet. In 2D, and it's XY ferromagnet because this is nothing but XY interaction. I should, sorry, it should be minus sign. Okay, so how to get the ground state? Or, as you said, almost ground state. So the idea is the following, that we start with the H naught, which, of course, what is, sorry, forgot to say that what is always possible, of course, is to have single fields acting on the cube. So let's start with the H naught, which is sum over H naught minus I to the I plus, well, X plus Y. That is a staggered configuration of fields in X and Y direction. That is, we have fields up here, down here, up here, down here, up here, right? And no term, no interaction term at all. We just didn't switch them on. Then we do the following. We, as a function of time, we decrease the field. Yes, sorry, very importantly, the initial state is the product of up and down spins on even sides and up spins on all sides, so that this psi naught is trivially the ground state of this Hamiltonian. Absolutely. Then, what we do, we decrease H naught and simultaneously increase J. So that at the end of this procedure, at T naught, we are arrived at the Hamiltonian that we want. So, of course, if we do it sufficiently slowly, we'll get the ground state adiabatic. The question is how, if we can do it in practice, right? Because in practice, we are limited by the lifetime of our system and so on. So then, so what are the times that one needs to, what are the times for what is the times that one need to get the ground state? Well, as my colleagues showed, well, one cannot get exactly to the ground state, but one can get to the so what suppose we get to the state which is not the ground state but a low temperature state, T less than J. What we expect then? Then we expect, because it is XY ferromagnet, we should have some number of vortices. So as a result, the correlation function of the spins in this state will be exponential of minus x at what? R to 0, R or psi, right? So what they can show that one can achieve psi or the order of the system sense, practically. One cannot really achieve psi, which is sort of infinite, but the problem, as we understand it, is that it's very difficult to get rid of the last vortex in the system. Because you decrease the concentration of vortices when you do it slower and slower, but eventually one guy remains, and it's very difficult to push it out.
Oh, one?
Well, maybe two. No.
But it is important. Two can just annihilate.
Yeah, probably it's one. I don't know then if there is analysis showing that it's just one. Probably it's just one.
Can I ask you?
Oh, of course, it's superposition, right? It could be one vortex in this direction, it could be one vortex in that direction. It's a quantum system after all. So
Why choose just this state? Because you somehow want to have a ferromagnet, right? You would say, yeah.
Yes.
Why choose an antiferromagnet if you actually want to stabilize the ferromagnet?
oh, because it's antiferromagnet. What we want is that
But your
the
J
magnetization in the direction is 0. Because if it is really ferromagnet in XY, magnetization in Z is 0, and remember that for us it's always crucial to have the error mitigation process. So we want to deal with the systems with a well-defined magnetization in the direction. In principle, you're right that it might be better to start with, let's say, sigma x, right? But then we do not know how many particles we have, and we will be completely swamped by the processes in which somebody decayed. So that works reasonably well. We can see that if you talk about the energy of the system, we get very close to the ground state. Not exactly, but low enough. So let me just quickly tell you about these problems, which I believe this problem that I believe is very interesting. The problem is that, and very natural for this system, in principle, that if we have a Bose liquid, then the first thing that you think that we know everything about Bose liquid, what can be more boring, but not really, because there could be a situation in which there is a parameter Rs. What is Rs? Rs is a ratio of potential energy to kinetic energy. So kinetic energy is, of course, temperature, and potential energy is, or actually kinetic energy for a thermal system will be a Fermi energy, but the potential energy is given by the interaction, and interaction in principle will be very large. So if we have a full control of the theory, if this parameter Rs is small, be it for fermions or bosons, we know that's a textbook. So for large Rs, of course, one expects that eventually we form a crystal, because if the interaction is largest guy on the block, then and we just have to minimize the interaction, and the minimized interaction is always means that we put our particles, Bose or Fermi particles, somewhere. However, it's known, again for ages, that especially in 2 dimensions, it's very easy to melt the solid state formed at large interactions, and as a result, Rs can be quite large, but still the system does not melt. Sorry, the system does not condense into a crystal. And as a result, there is a very broad range of parameters for the kinetic energy in which the sorry, there is a very broad range of parameters for which the energy is relatively large temperature, so that it is the positionization does not happen, but it's small, so that much smaller than an initial interaction, and there is sort of the liquid becomes something like a moss. So what we know about it is very little, surprisingly. So that in all time, what we know is that skip that. So it will take definitely too long. So what we know is that the energy, well, purely empirically, just from the studies of liquid helium, we know that the entropy of this liquid helium follows very strange law, like this one, in this range of parameters, in range of temperatures, roughly speaking, between couple of degrees and whatever is 50. So, and we also know that the transport is very unusual. That is, viscosity is linear in temperature, which reminds us this old puzzle of the high temperature superconductors, in which we know that the resistance is linear in temperature and there's absolutely no explanation about it. So that's the problems sort of known forever, and the point is that now let me skip all that because I don't have time to talk about it. That there is a normal phase of Bose liquid, and of course it's very natural to study this problem with our spin system, because the spins can be for a small magnetizations that we discussed before. Small spins are indistinguishable from the Bose particles with very large interaction. So I think that at this level I want to just conclude, because I would like to skip the rest. Yes.
Very last statement you gave. Is this some exact statement? This I don't know. Is this some exact statement? You said zero magnetization spins.
No, sorry. I should say that if I have magnetization close to -1, right? That is, if magnetization is magnetization. Well, let me remember that I introduce this quantity which is n, which is sigma z plus 1/2, right? So if this n is much smaller than 1, or on average, of course, right? So if this n is much smaller than 1, I can view my spin, my particles as basically bosons with low interaction. Sorry, with a high interaction, because they have hard force. Yeah. So
some kind of a dilute thing.
Yeah, and of course dilution is in my hands. I just do not want this parameter to be 0, sorry, 1/2, because then I start to get the commensurate phases. But I can have this anything 1/3, 1/6, and so then I really expect to form some sort of Bose gas, some Bose liquid, but then again interaction is strong and kinetic energy is small, and if we do not have a formation of some boring crystal, we do not choose a filling which is, I don't know, 1/4 or something like that, then we can address this interesting problem of the semi-quantum liquids that were never discussed properly. All right. Yeah. What?
Last statement is very funny.
Ah, yes, right. Yes, because that's what I wanted to say in the very beginning, just wanted to bring this to the end, that suppose we do something and observe something interesting in our simulation, let's say, of this problem for large sizes, and actually large sizes here are crucial because we need a large number of bosons, and the bosons cannot be too tight, otherwise they form a crystal, so we really need mixed systems. Suppose we observe something interesting, how on earth do we check that? And so it's only if we do the same experiments with different quantum computers. Which I think is very reasonable. Of course, the best thing will be to compare our superconducting device with the neutral atoms or something like that. But they have very different systems. Very difficult to find to get the same Hamiltonian. But even if you don't do that, just compare different superconducting circuits with each other, I think it's quite useful. Okay, that ends my talk for today. Any questions?
Questions to the lecturer? No? So I'm glad to see that number of people expand during the lecture, and let's say thank you to Professor Lev Ioffe for his lecture course, or this is the end of his lecture.
Yes.